For our project, we decided to talk about Kirchhoff's law. So Kirchhoff's law actually has two parts. The first law is the loop rule, and the second law is the junction rule. Later in this video, we will go into detail about each of the two laws. Before getting into that though, we wanted to discuss some basics and give some background information. In a circuit, current, measured in amperes, travels from the positive end of a power supply to the negative end of a power supply. We also know that the opposite is true for electrons. They travel from the negative end to the positive end. When we have a resistor set up in series in a circuit, it can change the potential energy. When the electrons enter the resistor, the voltage will be higher than when they exit, meaning there is a drop in potential energy. Let's say we have two resistors in a series. The first resistor will have a voltage of I1 times R1, and the second resistor will have a voltage of I2 times R2. Once we have found the voltage in each resistor, we can find the total change in voltage, which will be equal to V1 plus V2.
Let's say we have this circuit. The current flowing through the first resistor is called I1. The current flowing through the second resistor is called I2. And the current flowing through the third resistor is called I3. We can see there's a junction between I1, I2, and I3. This is where the current will separate. The junction rule states that the current entering a junction is equal to the current that leaves a junction. Here, we can see that I1 is equal to I2 plus I3. In this first example, I1 is equal to 10 amps. If I2 is equal to 5 amps, we know that according to the junction rule, I3 will be equal to 5 amps. However, if I1 is equal to 10 amps, I2 could be 2 amps, and therefore I3 would be 8 amps. The current will depend on the voltage and the resistance at a specific point in the circuit. We only need to remember that the current entering a junction is equal to the current that leaves the junction.
In any loop of a closed circuit, there can be any number of circuit elements, such as batteries and resistors. The sum of the voltage differences across all of these circuit elements must be zero. This is known as Kirchhoff's loop rule. Voltage differences are measured in volts. When the current I in the loop is given in amperes and the resistance of circuit elements is given in ohms, the voltage difference across a resistor can be found using the formula V equals IR. To sum up what we have so far, we know the sum of the voltage differences around a circuit loop has to equal zero. We also know to find the voltage difference, we use the formula V equals IR. The circuit drawn above contains 3 resistors and 3 different currents because of the junction rule. Because of these factors, I am able to form 1, 2, and 3 different loops. You can decide if you want these loops to go clockwise or counterclockwise. I prefer to follow the currents. Now, if you're following the current through a resistor, you should know that the voltage difference will drop. If you're going opposite of the current, then it will rise. The opposite is true when you're going through a battery. Now remember, if you're trying to find the voltage difference, V equals I times R. Kirchhoff's loop rule, junction rule, and the equation V equals I times R can be used to determine the intensity, resistance, or the voltage of a circuit.
What we see here is an example of a circuit with 3 power sources, one of 2 volts, one of 5 volts, and one of 6 volts. We also see 3 resistors, one of 4 ohms, 10 ohms, and 8 ohms. Now that we have decided the direction of our loops, we can draw our currents. We notice that at point B, I1 divides into I2 and I3. Also, at point A, I3 and I2 add up to form I1. Let's take a closer look at loop 1. We'll start at the power source of 6 volts. We can see that there's a potential drop. Moving on to R2, there's a potential rise. For R1, a potential drop, and for the last power source, we see a potential drop of 2 volts. With this information, we can come up with this formula. We start off with minus 2 minus 6 plus 10i2 minus 4i3 equals 0, which then gives us minus 8 plus 10i2 minus 4 in parentheses i1 minus i2 equals 0. The i1 minus i2 is what we came up with earlier, which then leads us to minus 8 plus 10i2 minus 4i1 plus 4i2 equals 0, and finally we get 14i2 minus 4i1 equals 8. Now moving on to loop 2, we'll start off at power source with the 6 volts. It goes from the negative to positive, which is a potential rise. This then leads us to power source number 2, which is 5 volts and is also a power rise. Moving on, we go to R3, which is 8 volts and is a potential drop. And finally, we reach R2, which is also a potential drop and 10 ohms. This then leads us to get our second equation, which starts off by being 5 minus 8i1 minus 10i2 plus 6 equals 0, which is then 11 minus 8i1 minus 10i2 equals 0, and finally 8i1 plus 10i2 equals 11. Now we're going to want to isolate for i1 by subtracting by 10i2 on each side and then dividing by 8 on each side, which is going to give us i1 equals 11 minus 10i2 over 8. Now taking the equation of loop 1 that we previously found, we're going to replace i1 by the isolated version that we found in the previous slide, which will give us 14i2 minus 4 in parentheses 11 minus 10i2 over 8 equals 8. When we calculate this, we end up finding that I2 is equal to 0.71 amperes. Knowing that I2 equals 0.71 amperes, we can plug it into the formula I1 equals 11 minus 10I2 over 8 and solve for it, which will give us I1 equals 0.49 amperes. With the formula I3 equals I1 minus I2, we can solve for I3 by replacing I1 by 0.49 and I2 by 0.71, which will give us minus 0.22 amperes for I3. Now combining our answers, we found that I1 equaled 0.49 amperes, I2 equaled 0.71 amperes, and I3 equaled minus 0.22 amperes. The minus only means that I3 is opposite to the direction assumed by the diagram.